In this video, we will talk about what sigma notation is. So sigma notation is some shorthand notation for sums. Okay, so I want to begin by defining what it is. So if I write the following symbol, this is the Greek letter sigma, and underneath it I'm going to write I equals m. Above it I'll write n, and next to it I'll write a sub I. So I'll explain what this means, but note that this symbol is the Greek letter sigma. That's where the notation gets its name from, sigma notation. Okay, so what does this mean when I see it? Okay, so this equals, and what I do is I first start by plugging in the value for I that I see written at the bottom. So I see I equals m here, and I'm going to plug that in where the I is. That'll give me a sub m. And then I plug in the next integer up, which would be a sub m plus 1, and then the next integer up, which would be a sub m plus 2, and then I keep going like this, plus dot 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 plus, until I reach the integer that's written on the top, n. And I plug that in and I'll have a sub n. So in this formula, the m and n are integers. The m and n are integers, and I is called the index of summation. The index of summation. Okay, so to get practice with working with it, I think it's easiest to look at examples. So let's evaluate the following sums. In part A, we have this sigma. So the way I read this is I say the sum from I equals 3 to 6 of I squared. Okay, so the first thing I do is I plug in the I value at the bottom, which is 3. I plug that in, I get 3 squared. So that's coming from when I equals 3. And then I plug in the value I get from plugging in one integer up, which would be 4. So 4 squared. And I start to add these. So this is coming from I equals 4. And I keep going like that, plugging in successive integers until I reach the integer on the top. So next I'll do 5 squared. And then I plug in 6 and I get 6 squared. And if I were to work this out and add these together, I get 86. And that's what that notation means. Okay, so let's do another example. Part B. This time I have the sum from k equals 4 to 10, so different variable, that's okay, of 5. So first I have to plug in k equals 4 in, but there's no value, there's no k in this formula, so there's no place to plug in 4. So when I try to plug in 4, I just get 5. That's the output that I get. Okay, and then I plug in k equals 5. And when I do that, again, I'll get 5 out. So we start to add these. And then I'll plug in k equals 6. And when I plug that in, I get 5 again. And we keep going like this. So plugging in 7, I'll get 5 out. Plugging in 8, I'll get 5 out. Plugging in 9, we'll get 5 out. And then plugging in 10, we'll get 5 out. So altogether, we have 1, 2, 3, 4, 5, 6, 7 of these 5s. So we'll then put 5 times 7, which is 35. Okay, so let's do one more example. So part C, let's say I have the sum from j equals 0 to n of negative x being raised to the 3j power. Okay, so I start off by plugging in 0 for the j, so I'll get negative x to the 0. And then I plug in 1 for the j, so that'll give me plus the negative x to the 3. And then I plug in 2 for j, so I'll get negative x to the 6. Plug in 3 for j, so I'll get negative x to the 9. And then plus dot 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 plus. Finally, when I plug in n for j, we'll get negative x to the 3n. And we can simplify this a bit. So something to the 0 power would be 1. And the negative x cubed is going to be, I can pull the negative in front because this negative being cubed will give me a negative. So I'll get negative x to the 3rd like this. And negative to an even power like 6 will give me a positive. So I'll get positive x to the 6th. The next term will be negative, because I'm raising the negative to an odd power, so negative in front, so minus x to the 9. And then I keep going, plus dot 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 plus. The last term, I'm not sure what the sign is going to be, so I'll keep it as negative x to the 3n, because we don't know whether n is even or odd. So one note about this is that I'm using the fact that something to the 0 power, I used that for the very first term, something to the 0 power, in fact, let me write it like this. Let me pick a different variable. A to the 0 equals 1 if a is not 0. 0 to the 0 is undefined. That's a fact from algebra. So implicitly in this problem, I'm assuming that x is not 0. Because if x was 0, this very first term would be undefined. So next, I want to state a key theorem that'll give us a bunch of nice formulas involving sigma notation. So the theorem begins by saying, let c be a constant and n be a positive integer. Then, so the first property of the theorem says, if you take the sum from I equals 1 to n of 1, well, what does that equal? Well, here, if you plug in I equals 1 into this, you get 1. If you plug 2 into it, you'll get 1 again. And if you keep going like this, you'll get plus dot 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 plus. Finally, when you plug n into it, you'll get 1 again. So overall, you're adding 1 to itself n times, and that just equals n. So this will just be equal to n. So this was underneath, we actually just explained the reason behind this, behind why this is true. Okay. Second property, what if I have the sum from I equals 1 to n of I? Well, if I start to plug in values, if I plug in 1, I'll get 1. If I plug 2 into this for the I, we get 2. Plugging in 3, we get 3, and then plus dot dot dot, plus. Finally, we plug n in, and we get n. So what is this sum? Okay, so it turns out this whole thing equals n times n plus 1 over 2, if we were to add the first n positive integers. So there's a very nice and short but famous proof of this. So I want to give you all that proof. So this is proved. A version of this was proven by a mathematician named Gauss when he was in kindergarten. And I say a version of this because in kindergarten, so the story goes, Gauss's teacher asked the class to add up the first 100 positive integers. So they asked the class to add up 1 plus 2 plus 3 plus dot dot dot, all the way up to 100, the first 100 positive integers. And he found a very clever way of doing it. So that constitutes the idea behind the proof I'm about to show you. Okay, so the idea is, let's let S be this sum. 1 plus 2 plus 3 plus dot 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 plus. And the number before n would be n minus 1. So n minus 1, and then we'd have plus n. And then what we can do is, let's write S again, but with all the terms in the reverse order. So let's start by writing the n, and then n minus 1. So we're going to go in descending order this time. The next term would be n minus 2, and then plus dot dot dot. And at the end, we'd get down to 2, and then 1. So if we look at these two lines, one nice thing that happens is, if you look at the terms that are directly above and below each other, so I'm going to start to circle these pairs. Circle all these pairs. Notice that when you add each pair together, they have the same sum. So if we add these, what would we get? On the left-hand side, s plus s is 2s. On the right-hand side, 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. And if we keep going like this all the way down to the end, the last n plus 1 is n plus 1. So how many of these n plus 1s do we have? How many circles were there? Well, there were n circles. So this is happening n times. So we get 2s equals. So if this number is being added to itself n times, that is just n times n plus 1. And now, remember what we were trying to get at the beginning of this. We were trying to figure out what s was. S was the sum of these first n positive integers. And I can just divide by 2 and I have s. So if I do that, we get s equals n times n plus 1 divided by 2. And that's the formula right there. We've just proved it. Okay, so I'm going to put a smiley face there. So we have proven this result, the sigma notation formula. So that's pretty cool. Okay, so we are on to property 3. So if I have the sum from I equals 1 to n of I squared. And if we plug in values, plugging in 1, we'd get 1 squared. Plug in 2, we get 2 squared. And if I keep going like this, we'll have plus dot dot dot. And finally plugging in n, we'll have n squared. So this is the sum of the first n positive integers squared. This ends up being n times n plus 1 times 2n plus 1 over 6. Okay, so one of the most standard proofs of this involves something called induction. And induction is beyond the scope of our class. This is something that you might see in a discrete math course. So I'm not going to give the proof of this. This is just a formula that we can use. Okay, so there are 2 more formulas, but I think these last 2 are going to be a little bit more kind of what we'd expect to happen. So the sum from I equals 1 to n. If I have a constant times my a sub I term, what I can do is I can pull that constant to the front. So I'll get the c in front and then times the sum from I equals 1 to n of a sub I. And there's a similar formula if I was adding or subtracting 2 things in my sigma notation. So if I have I equals 1 to n of, and then I have a sub I plus or minus some other formula b sub I, I can split this up into 2 sums. The sum from I equals 1 to n of a sub I, and then either plus or minus the sum from I equals 1 to n of b sub I. So the main reason I'm showing you all these formulas, these sigma notation formulas, is because they're helpful to us in finding the exact area under a curve, which was a question that we were considering in the first videos of this section. Okay, so I'm going to draw a picture. So imagine I have some axes, and then I have some curve. Some axes, and I have some curve, and I'll call this y equals f of x. So let's say that we want to find the area under this curve over some interval from a to b. So I'm going to split this up into some subintervals. So I'll go some subintervals here. And what I'm going to do is I'm going to split this up into n subintervals and use right endpoints. Whoops. Sorry, for some reason the graph got shifted on me there. So I'm going to use right endpoints and then n subintervals. Okay, so let's draw some right endpoint rectangles here. So for the first subinterval, I'm going to draw up from this first endpoint until I touch the curve, and then the top of the rectangle, and then down. And for the remaining rectangles, I'm going to go more quickly through it because we've seen this a few times now. So next subinterval until I hit it, top, next rectangle, next rectangle, next rectangle, next rectangle, second to last one, and one more, and there we go. So we have all of our rectangles. So now I'm going to introduce a little bit of notation. So this leftmost endpoint here, A, I'm going to call this x sub 0. The tick mark after that, I'm going to call this one x1. After that, I'll call it x2. After that, I'll call it x3. until I get to b, and b, I'm going to call this one x sub n. So we go up to x sub n because we have n of these rectangles. In fact, let me write that x sub n better, x sub n. Okay, so in this formula, sorry, in this picture here, delta x is this distance, delta x. And delta x is the length of the whole interval, which is b minus a, and then divided by how many rectangles we're going to use. In this case, we're going to use n rectangles. All right, so moving that r sub n down a little bit, let's start to add up the areas of these rectangles. So the area of the first rectangle would be the base, which is delta x, times the height, and the height is going to be f of x sub 1. So whatever I get when I plug x sub 1 into my function, because x sub 1 is the right endpoint. For the next rectangle, the base is delta x, and the height would be f of x sub 2. And if we keep going like this, we'll get plus dot 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 plus last rectangle, rectangle number n, would be delta x times f of x sub n. And this is something that we can express really nicely in sigma notation. This is going to be the sum from I equals 1 to n, because we have rectangles numbers 1 up to n, and it's delta x times f of x sub I. That's the same thing as what I had above it. And I could check it. I could check by plugging in these values for I. If I plug in I equals 1, I get delta x f of x1, and that's the first term. Plugging in I equals 2, I get the second term. Plugging in I equals n, I get this last term. Okay, so this would be how I compute the area of n rectangles in general. So now, if I want to get the exact area, because that was sort of our big goal, finding the exact area, what I would need to do is let the number of rectangles go to infinity. Because the more rectangles I have, the narrower they get, so the narrower this interval gets, and the amount that each rectangle is off by, like for example, this rectangle is off by this much, or this rectangle is off by that much, that gets smaller and smaller and smaller, gets closer and closer to 0 the more rectangles we have. So we're going to take the limit as n goes to infinity of r sub n, which is the limit as n goes to infinity of the sum from I equals 1 to n delta x of f of x sub I. So in the next video, we will compute these limits. These are limits of Riemann sums. Compute these in the next video. And one of the things that's really going to help us with computing what this actually is having nice sigma notation formulas like the ones that we just got above this. In terms of our goals for this section, we have finished our third goal. We've talked about what sigma notation is. In the next video, we'll do an example where we actually find the exact area under a curve using this notion of a limit of Riemann sums, which we just finished talking about.